Thank you very much. Thanks to Emily and Steve for inviting me. I've enjoyed the centre and really loved the atmosphere of Davis as well. Controversial, I don't know about that. I've disappointed women before. And I may do again. But I did really enjoy the last slide of Vince Clarke's talk because it exemplified what I want to be for the next hour, which is your trough of disillusionment. I think it's long overdue, and I think it would do the field a service if we took a head dive into that trough of disillusionment and swam around in it for a while. Before I do, I'd like to. I've been sat at the back all day, and you have a talk prepared, and then somebody gives out, oh shit, I was going to say that. So you change a slide, and you think, oh, that's really interesting. I'll make a point about that. So I've got quite a few ad hoc things, and the first comes from Michael Nietzsche's talk. I wanted to offer some other historical insights. This is from 1751, and I think the very first use of electrical magnetic stimulation to produce phosphines. There was a French surgeon called Charles Leroy, and he had a patient, a 21-year-old blind Englishman called Granger. Granger was blind, and they thought, well, if you're blind, then we'll stimulate the eyes and make you see again. So they passed a voltage across Granger's two eyes, and he died blind. In 1896, D'Arsonval, a famous French physician, this is D'Arsonval here, these are his RAs, so those of you who are worried about tenure, just chill out a little. This was an attempt to try and understand people's reports of vertigo and dizziness and phosphines when they were working in big power stations that were being built at the time. So Igor here switches the flicks the switch. These guys let go, and the guy in the middle will report. He also reported phosphines, visual flashes of light. Now, I've shown these two on this next slide, which was from 1914 when they were trying to stack magnets up to get a field which would penetrate the skull and reach the brain. So far, everything had been retinal. We know that post hoc, that everything had been retinal, and the picture of Sylvanus Thompson that Michael showed you was also retinal in its effects. And the reason for showing you these is that really, although transcranial magnetic stimulation and DC stimulation look like very simple piece of equipment, and they are in essence simple, it's been a long, hard battle to find ways of stimulating the human brain. And we've also been here before. We've been here before with the hope that brain stimulation will be of some potential use to us. So this is from, I think, the New York Times in 1912. Science finds a new fountain of youth for tired, lazy and nervous people. And what this is that people were interested in the effects of electromagnetic fields. So you could buy these little generators, and you could sit between them and expose yourself to electromagnetic fields, and you could buy belts that would expose your children to them as well to help improve your children's cognition. So we're not thinking of anything new here, and even in classrooms there were experiments in classrooms where people had these electromagnetic generators in the front of the classrooms so that you could make your children smarter. And I guess we're here because it didn't really work. And it's not working that I partly want to talk about now. What I want to concentrate on are what kinds of things we tell ourselves in the lab, what kinds of things we think are interesting in the lab, how these might translate to any effects in the real world. And I think one of the things we haven't addressed today is that deep division between the 10 or 20 milliseconds that we get all excited about. If we get 100 milliseconds, we share them out and have two papers between us. Or that 5% increase. What does that really mean in the real world? When somebody's sat in a dark room, pressing a button as their motor response, looking at a screen on which we pride ourselves contains objects that they've never seen before, so that they can be naive. Just think of the field of visual search, for example. We pride ourselves that everything we do is with naive subjects. I've never been here before, but you're dressed like an academic audience, you're the same size, you're pretty much in the same array, you look just as bored, the arena is pretty much the same. I bring lots of statistical information to this scene. We don't live in a naive world, and yet we pride ourselves on this in experiments. It's a bizarre little thing that we do. And the world also doesn't exist at 57.3 centimetres. That comes as a shock to lots of people as well, because our psychology students can't do algebra, trigonometry rather. So I do want to address that. I also want to raise the question, and we'll talk about ethics at the end, and I'm sure it'll come up in the general discussion, about what we want from intervention studies. Do we want to learn about fundamentals, or do we want to change people's behaviour and opportunities in the world? And we haven't, I think in the literature, we try and have our cake and eat it, and we haven't really said what our aims are, and don't say what our aims are in all our studies. I do want to address and have a think about some of the dependent variables that we use and readdress that lab and real world distance. And I also want to address the question, before we go on to ethics, of even when we get an effect, even when we show that direct current stimulation or any other form of stimulation can have an effect on the brain or on performance, does that mean that we should do it, or does that mean that we should want to do it, or does it just mean that the potential is there and that we should then use that as basic scientific knowledge to find some other ways of creating interventions? So the big negative that I really want to emphasize is that we have all these studies that say enhancement in X, enhancement in Y, and we take them at face value, but we haven't really got a systematic way of asking what do we want from that paper and how should we assess that paper. And what I'm going to do over the next few slides is take 3 or 4 case studies of papers. I've taken them for 2 reasons. One is that 2 of them are from my lab, so if I can criticise my own papers, I can say what I like about anybody else's. And the other reason is that in a recent article about the power of brain stimulation, some of these other papers have been cited as examples of just how big a deal it can be. So I think those would be the best papers to show how just small a deal they are really, and maybe we should rethink about things. So when we look at a paper, I think we should ask a number of things. One is, what's the montage? Where have we put those electrodes, and what does that allow us to say physiologically about the effects that we're having? The second is the intensity, and even though Michael, as he always does, tells us about the fundamentals and leads the way in understanding DC effects, even though he told us this morning that increasing the intensity and increasing the duration can actually reverse the effects of the DC stimulation, that has not been taken on in any of the discussions of any of the DC papers which have reported cognitive enhancements. The frequency, how often people should have it, I think also I want to discuss. I'm sick to death of papers which report a single intervention, one 20-minute intervention of direct current stimulation or TMS or any other intervention, and then say subjects were improved. What they mean is subjects were improved for the next 100 trials in the experiment that we've concocted for this particular for this experiment, and there is again not a big enough, a deep enough line drawn between those kinds of effects and the claims we make, and we do make them in the popular press about the effects of our experiments. Perhaps the second most important thing that I will say, in addition to discussing what we can say about the montage, will be looking at the controls that we have in experiments. I'm going to argue that a sham control is completely inefficient, and because we're interfering with the brain, it's a cheap way out of controlling for an experiment and leaves us unable to say what it is that we've done. In most of the experiments we've seen today, and most of the experiments I will talk about, have got a sham condition and an active condition. But that active condition doesn't allow you to say what you're doing. Are you warming up the brain? Is it the tingles? Is it anywhere on the brain that would produce the same effects? So I want to argue and hope that I can start to make people find a sham-only control unsatisfactory. It makes life harder, it makes publications slower, but I need fewer papers to read, so I'm not sorry about that. A physiological hypothesis. Sometimes it's okay to say, well, if we're helping people and these things work, we don't really need to understand the mechanism. And there are even cases of drugs on the market where the precise mechanism is not known. It was discovered by accident. The effects might have been something that they were using as a control. But I think in the spirit of being basic scientists, we do want to have that physiological hypothesis. So I will take a dim view of papers that don't fulfil that criterion, including mine, which will be first up. And behind this all the time is this question of how we parse behaviour. There seems to be this assumption that it's okay to take standard psychological tests off the shelf, put them into a brain stimulation experiment, and recycle the explanations about attention and working memory. And if you were to ask me, what have we learned fundamentally about cognition from direct current stimulation studies, I would say absolutely nothing. I cannot think of a single experiment which tells me something about the brain that I didn't know before. Most of the experiments have done what the early days of fMRI did, which is to take a well-known textbook experiment, show us something that we already believed, show it us with pictures, and now we're doing the same in direct current stimulation. So it is on that curve of I don't know what it was, the curve of hype or something. And I think we're right at the very, very peak of that right now. Somebody asked a question of Michael during the first talk, which was, what are your optimal settings? And Michael quite rightly said that he didn't know. And we can't possibly know at the current state of play in direct current stimulation because we haven't begun to explore the parameter space of montages. There are 2 or 3 montages that dominate all experiments. They're there because of historical accidents. There's a limitation of intensity up to 2 milliamps, historical accident. There's no principle behind that. There's a duration maximum of 20 minutes, historical accident, no principle behind that. Frequency, it depends. Usually 5 days is a maximum for training experiments. Let's say that's got something to do with there being a weekend at the end of those 5 days. It's a historical accident. Okay. Control sites and tasks. We've just got into a state in the literature where we are letting ourselves get away with weak controls, and we're not putting ourselves up against the wall and asking each other hard enough questions at the review stage in papers. And I will have a lot more to say about this. Physiological hypotheses. Cognitive scientists like me are the worst. We have this simple push-pull model of the brain in which the anodal electrode is excitatory, the cathode electrode is inhibitory, and that gives us infinite degrees of freedom when we add that to our attentional models of attention or working memory or whatever it is that we're working on. Perhaps this would be a good time to say that I'm a believer, that I think that there is a lot of scope for real progress, clinical progress and basic science progress using DC stimulation. But what I perceive at the moment is a situation that's akin to where we were with transcranial magnetic stimulation and depression 15 years ago, which is that there were lots of little studies, some of which were replicable, some of which weren't, which actually created so much noise relative to signal that the uptake of transcranial magnetic stimulation for depression was delayed rather than enhanced. And what I perceive in the literature right now is a signal-to-noise ratio that's extremely low. So this isn't, there's no cynicism behind this at all. There's optimism behind this. I think we just need to do a little bit of laundry in order to get ourselves to a better starting point for our experiments. So what kinds of claims, to be a little bit more negative first, what kinds of claims are made about DC stimulation or transcranial magnetic stimulation or anything else? That it can improve perception, reasoning, decision-making, reading, numerical skills, addictive behaviours, moral decisions, creativity, memory, schizophrenia, migraine, schizophrenia. I say schizophrenia, that's for the other side of the personality. That is an accident. Visuomotor skills, epilepsy, aphasia, dystonia, stroke, pain, multiple sclerosis. Do me a favour. This is with electrodes being on the prefrontal cortex, the prefrontal cortex, the prefrontal or a parietal cortex, the prefrontal cortex, the prefrontal cortex, the prefrontal cortex, the prefrontal cortex. Something's got to give. It cannot all be true. And this is where the control conditions come in. Just to preempt something that I will say, for example, My earrings don't fit. If you have an experiment in which you are looking at people's moral decision making and you're stimulating the prefrontal cortex, think of what we do if that was just a pure behavioural psychology experiment. We'd want to know, how long was the stimulus presented? Was it a verbal response? Were the instructions, did they emphasise anything positive in the instructions? Was it a male experimenter with a female subject or a male experimenter with a male subject? We'd want to know all sorts of things about those experiments. We'd want them controlled. But we have, I've only picked on this one because it's at the right level. There's nothing special about it. We have an experiment on moral decision making that stimulates the prefrontal cortex. But moral decisions contain aspects of reasoning. Do we control for that? None of them do. They contain aspects of perception of the stimuli that you use in that moral decision presentation. Do we control for that? No. You might have to read the instructions. Do we control for that? No. There's memory involved in the moral decision-making task, which is also involved with the prefrontal cortex. Do we control for that? No. And this is why the sham control is really unacceptable. We need to do two things. We need to stimulate in other areas, and we need to have controlled tasks. And almost none of the experiments that I show you today will do that. And they're not from small labs, you know, they are from the labs that you would read first if you were thinking, I'm going to go and do a DC experiment. We also have to ask how long the effects last, and we're very hazy on that. How practical are they? So stillness, a word there. Let me explain everything that, at the risk of embarrassing Michael, I think if I was to say read one person's work on transcranial direct current stimulation, it would be Michael Nietzsche's. He and Walsh have basically built the field. But even Michael's work is almost entirely built on recording from this muscle or this muscle when the subject is maintaining themselves very still and very calm. So let's take the most fundamental finding in DC experimentation, that when you apply anodal, you get excitatory effects, and when you present cathodal, you can put it on the same side if you like, you get inhibitory effects. If during the experiment the subject is going like this, those effects have gone away. So I now want to ask you, think about cognition. In your experiments, you're asking people to be cognitively active. What right have you got to still think that your anodal effects are anodal and your cathodal effects are cathodal? Not only can shaking the hand remove those classic effects, it can reverse those classic effects. So again, what right have you got to think that your electrode is even being anodal when you've got somebody doing a cognitive task? We can't measure there isn't a physiological signal of the brain going like that. Maybe the brain goes like that, I don't know. But the brain is certainly active in the same way as those muscles would be active. So the same way as the brain regions governing those muscles would be active. So I think we really should be thinking about reducing our level of confidence about what we're doing in stimulating anodally, cathodally, and automatically assuming that means that we're stimulating excitatorily or inhibitorily. And what are our best examples? Let me take you through some of them. I was amused when Roy showed this Cohen-Kadosh study, which did cause a big splash when it was published, and it was done in my lab while Roy was a postdoc there. And it's the first study I'd like to take apart, really. Can we speed up? Because it doesn't say what we said it says, it doesn't show what we said it shows, and it doesn't show what people think it shows. Which is our fault, I guess, for saying that it showed something that it didn't really, and I apologise. But, you know, the reason that I came to this paper, I was getting really frustrated with literature, and I was looking through it, and I was starting to think there's something wrong with all these papers. I wonder if the same thing is wrong with mine, because I'm just in the community. I have the same mindset as the rest of you. Why shouldn't I pick up the same bad habits? So here's the first bad habit. We stimulated over the right and left. It's the other one. The right and left parietal cortex. So we have anodal, cathodal, or we have anodal, cathodal. Given what I've just said to you, and we stimulated for 20 minutes, so I want to tell you two things about this. Given what I've just said to you about anodal, cathodal, not being anodal, cathodal when the brain is active, we actually have no idea that our anodal and cathodal were anodal and cathodal, and neither does anybody else who has a bilateral montage like that and stimulates for 20 minutes. The second thing we don't know is what the interactions were between the two hemispheres. We know that if you stimulate the left motor cortex, you're going to have an effect on the right motor cortex, but we somehow, and not just in this paper, in the whole community, assume that when we stimulate anodally over this cortex, there's going to be a discrete anodal effect over this area of the cortex. But if it's communicating with this, then we should be thinking about whether we're starting off with a more inhibited region of cortex here. That's even if we buy into the assumption that the anodal stimulation is indeed excitatory. So we can't say anything about the excitatory or inhibitory effects, which means that we haven't got a mechanistic explanation for our experiment. I didn't realise that until 2 years after we'd published it, and I'd thought about it harder, but I think the point of thinking is to change your mind. So then we claimed that we improved post-test, but let's have a look at what we improved. So this is the test, just to remind you. I'll run through it very quickly because Roy went through it in more detail than I was ever planning to. We give people these symbols to learn as numbers over 5 days. They do 20 minutes of learning with stimulation, and they carry on for another session of about an hour and 20 minutes. And then we gave them a Stroop test, which was a symbolic Stroop test based on these, and we also gave them a standard numerical Stroop test. And we also gave them a spatial test of mapping numbers. I'll just stick on this. This is the Stroop test that we might have. Here you'd be very quick to respond because 4 is bigger than 2, and here it's physically bigger than 2. Here you'd be a little bit slower to respond because there's not an incongruency, but there's not complete equality between the numerical value and the size. And here you'd be slower to respond because you've got to get over the conflicting information that this 2, which is a smaller value, is actually bigger than the 4. And that was our test of mathematical cognition, or one of them. I'd like to say, first of all, of course, it's just a proxy test. We haven't got any demonstration that links to people's actual numerical abilities. So that's part of that lab real-world gap that we make an assumption about, and this happens a lot in DC experiments, and I guess in others, but I'm only concerned about DC experiments. And then there's this other plot here, which shows that over 5 days of training, the cumulative reaction time advantage was about 125 milliseconds, so about 25 milliseconds a day, which is very small. And what that really showed was that people with stimulation learned the digits after 4 days, but people without stimulation learned them after 5 days of training. So it bought you 1 extra day. So my contention here would be, we got very excited about it at the time, that it's scientifically still very interesting, but the claims that we made that it actually has something to promise for numerical cognition, I'm really not convinced about. And I think that's because our proxy measures of numerical cognition are exactly that. They're proxy measures, and we didn't establish that they would translate to real numerical cognition. So we got an effect which is good, and it's related to number, and that's the area we were stimulating, and I guess that's good. But it was indirect. There was no blinding, by the way, and I don't care if there are some experiments which show that blinding doesn't matter. It would be such a bad idea if we adopted that idea that blinding doesn't matter, and I think it's something that we should have done and we should do. We can't physiologically interpret it, and I don't feel so bad about that because I'm going to show you some other very big laboratories' works who can't physiologically interpret their work either. And our real-world gain was very, very small. So when we ask the question now, does this give us any reason to start thinking about applying DC stimulation in improving numerical cognition? I would say no, not really. It's very interesting in a cognitive sense if we start doing some of the controls for this experiment that we should have done, but it doesn't really give the promise that either we or indeed the popular press would lead you to believe. So we failed out in our montage. We had the worst possible montage, but it's the most popular montage in cognitive neuroscience experiments. We did okay in intensity, 1 milliamp. According to Michael's experiments, 1 milliamp, you probably are having excitatory effects under the anode and inhibitory under the cathode. Duration of 20 minutes, actually, because so now we fail again, because after 20 minutes, your anodal effects can become cathodal. Or the other way around, sorry, your cathodal effects can become anodal and can become excitatory. So not only does the interactions between the two hemispheres stop us interpreting the work, so too does the fact that after stimulating for 20 minutes, we can't be sure that our cathode electrode would be doing what it should be doing, or we would like it to be doing, even if everything else was okay. And our physiological hypothesis, although we had one and we stimulated the right area, I think it just has to be thrown away and we have to start again. So that's Walsh dealt with. Let's have a look at another area that's become had a high impact in the DC field, and also had a high impact in the popular press and in the promise for what we can do. And now we're getting into the areas of decision making and addiction. This is a paper by Boggio et al. In 2010 in European Journal of Neuroscience. They had a right anode, left cathode, left anode montage, dorsolateral prefrontal cortex. They had the Cambridge gambling task. This is interesting. They used older adults, 55 plus, stimulated at 2 milliamps for 15 minutes. So here's another surprise. Well, let's go through the data first, and then I can. So this is the kind of task. You have to guess where the token will be hidden, and if you guess it's under a red one, you've got more of a chance of being right than if it's under a blue one. But the rewards for these and the losses are titrated so that people can estimate your risk. How many risky choices are you going to make? And the claim of the paper is that with either right anode or left anodal dorsolateral prefrontal cortex, you made fewer risky choices. And when we calculated the points, it was the right anode stimulation that produced a bigger loss in people. People didn't make as much money. They didn't take the right kinds of risk. There's an interesting statement in the discussion. In this study, we used exactly the same methodology used in our study in healthy young subjects. They'd done a previous paper in which they'd given this task to, I think, 18 to 23-year-olds. And here we showed that stimulation of the same areas has an opposite effect in older subjects. It increases rather than decreases risk behaviour. Now, they do give some, to be fair to them, some theoretical explanations of that. They're clearly post hoc, but there's nothing wrong with that either. But this is an important thing to note for, again, the claims that we make in the literature about the effects of DC stimulation in the laboratory being translated to the clinic, because traditionally we almost always work on the 18 to 25-year-old brain, because those are the people we've got in our laboratories. If the effects of DC stimulation are going to give you the opposite effects in people who are older, and most of your patient population is going to be older, and that's another thing that we have to address in the literature. And almost everything in the literature makes the transition from these white, educated, industrialised, rich and democratic subjects. I don't know if you've seen the paper in Behavioural, to the patients who will be perhaps none of those things. So I think that's another thing that we have to be really very careful of when we make claims about what we can do. Can we learn anything about task specificity from this? Well, no, because there wasn't a control task. Now, again, making a decision like that involves perception. It involves a little bit of memory. It involves some estimation about value. It involves feedback about reward. We have to have some kinds of controls so that we can know. Gambling isn't a discrete entity that's got one place in the brain, and we could say there is a gambling function in the brain. And this study, and again, it's not a criticism of a special criticism of this study. It's redolent in the field. This study has completely failed to do any psychology. Physiological specificity out of the water because of the left-right interactions. In this case, because it's 2 milliamps. So here's another problem, as Michael showed when you in another paper in Journal of Physiology. I don't know if you showed the data today. When you go up to 2, it does. I've got it on one of my latest slides. When you go up to 2 milliamps, then cathodal effects can become anodal. So again, when we increase the current, we actually don't know whether our cathodal effects are cathodal. Now, just reflect on that for a second. That might mean that in this study they had a left left anodal effect, and they had a right cathode at 2 milliamps, which might also be an anode. So now they should have anodal. So they shouldn't have any differences between the right anode and left cathode stimulation condition. So physiologically, we're completely at sea. Translation to real-world application, well, this effect sizes, again, we all know this, we plot things very well so that we can show them in our best light when we're publishing, and that's fair enough. We want people to see what the scientific consequences are. But in this and in many studies, the effects are very small. And when you ask, how does this translate to how much money somebody would gamble in a task, or how many cream cakes this person would eat, or how many cigarettes this person would take, or how many bad moral decisions this person would take, there is not a single piece of evidence from the DC literature that anything that we've done translates to those real world kind of behaviours. And in some senses that's okay, because we when we're doing fundamental experiments where we're just trying to learn about mechanisms, then that's fine. But when the papers are written and we engage with the public, and I think this is the biggest ethical issue, is how we engage with the public, because people get the ideas about what these things can do from what we tell people. And when we write our papers about the translational possibilities, then I think we step over that line. This experiment then, it failed in the montage, it failed in the intensity because it went up to 2 milliamps. It failed in frequency because it was a one-shot experiment, and I think it's good to be deeply suspicious of something that works once in a laboratory for the duration of the experiment. There's no evidence that this would have had an effect that lasted after the experiment. It has no control site or control task, and the physiological hypothesis, I couldn't even bring myself to put an X next to it. This is a beautiful paper, one of Michael's, showing that when you increase the stimulation level of a cathode, cathodal effects up to 2 milliamps might sometimes become excitatory instead of inhibitory. It's just a deeply cautionary note that I think everybody going up to 2 milliamps has to take on board. I'm saying, one of my motivations for saying this is when I come to workshops is people want to do DC experiments and they think they can go away and just do DC experiments, and what happens is that it doesn't work and people wonder why, and these are the reasons that they don't work. These are the data from Michael's experiments. He did a bunch of physiological measures, none of which I'll go into, then gave 20 minutes at 2 milliamps, anodal or cathodal, and then did a bunch more of physiological measures, and that's what you see. The cathodal effects become excitatory for up to 60 minutes afterwards. Another one, smoking craving. I've presented this one to Felipe in a similar kind of talk, so I'm not telling tales out of school. Again, right anode, left cathode, bilateral stimulation. We now know it's worthless. Logic. They took an fMRI study which shows that there are bilateral activations involved in smoking craving, and then decided to do two different things to the dorsolateral prefrontal cortex. I don't understand that. It's a scientific point, and I'll move on from it. I can talk about it if people wish to. So we have no idea which stimulation did the job in this experiment. Let me show you the experiment. People were... Is that blurry to everyone else? Good. If it isn't, see your optician. It's blurry. Take baseline measurements of craving assessment, expose people to things that make them crave, movies and pictures of smoking-related paraphernalia, give them a cognitive assessment, craving assessment, stimulate for 20 minutes, that period at which you start to have to question whether your electrodes are doing what you think they were doing for the first 19 minutes. Then give another craving assessment and show them the movie again and assess them again. So you assess them at 3 different points, and what they found was very small effects, that after at this point, after the stimulation, there's an effect of left or right dorsolateral prefrontal cortex stimulation. But it's a visual analog scale, and it's between 5 3/4 and 4 1/2. I don't think that adds up to a cigarette, and neither do any of the authors I've spoken to think it adds up to a cigarette either. So this experiment, and the 3 experiments I've shown you so far are 3 of the most highly cited in the DC literature. They're 3 that people would look to for the methodology, for what to do when they do a DC experiment. It fails on the montage because we don't know what's going on in the left or the right dorsolateral prefrontal cortex.
Comment shortly.
Sorry?
If you put 2 or 3 slides back, we have a big return electrode in this case.
You have what, Michael?
They have a large return electrode in this case, and there is this large return electrode that makes this functionally inefficient when you see this large electrode.
That's true. Yeah, I didn't notice that.
So it's not, in strict sense, at least not aimed at bilateral stimulation.
Okay.
So they do another stimulation of one hemisphere.
So here's an interesting, this is the kind of thing that we already don't know. What would you predict would be would you predict that the cathodal effects after 20 minutes would be any different than with a smaller?
2 milliamps? Or
2 milliamps.
Then we are with another misconception. If it would have been done with 1 milliamp stimulation,
yeah.
so you have this 10 per 10 centimeters return.
Yeah.
Then this should be effective.
With 1 milliamp. But with 2 milliamps?
We don't know.
Exactly.
This is another misconception. Many studies where they say, okay, we have this 2007 paper from our group where we have this 10 per centimeters return electrode. This has shown to be functionally inefficient because of reduced current density, and because of this shouldn't be effective. So we might have, or we should have a difference in efficiency somehow, but we can't say it's 2 milliamp in this size that it's completely inefficient.
Yeah. So on other things in the experiments, apart from having small effects, there's a nice bit in the discussion where they say we assess people's mood, but there were no effects on mood, so we can't explain our effects based on changing the people's mood, which made me laugh when Roy was presenting his experiments, because he showed from the same group the same electrode configuration changing mood in depression. So we should worry about these things. Okay. So far what I've really tried to concentrate on is this distance between lab and planet Earth. And in a sense, all these experiments can still be interesting in a scientific sense. If I've sounded a little harsh on them, it's because they have been taken to be papers that show some of the best promise for the effects of DC in a clinical or a real world setting. As scientific papers, they're just like any other papers. We can rerun them. We can fix the things that those papers did wrong. But this is, I'd like to think that people would use this as a kind of a little rubric whenever they're thinking about assessing or carrying out a DC stimulation experiment in cognition. What's my montage? What can I say physiologically from that montage? Is my intensity doing what I think it's doing? Is my duration such that my stimulation will carry on being excitatory and inhibitory? How many times should I do this? Should I be satisfied with changing people's performance for 20 minutes afterwards? You might not need a physiological hypothesis. It's always better to have one. Controls, we must have a task control. So far, the experiments I've shown you haven't had a task control. You wouldn't have it in a neuropsychological experiment. You wouldn't allow somebody to say, here's a patient who has lost their ability to perform some attentional task. You would say, that's very interesting. What can the patient do? You want to know what the specificity of that is, and I don't understand in a neuropsychological context why we've allowed ourselves in this field to eschew that constraint. Okay. It just reminds me of the... I guess I do want to make this point. My ears have fallen off again. That there is, I think, because the literature is partly dominated, this literature, by medical people who really want to make a difference with the stimulation, that we've adopted the randomized control trial logic, and I think that's fair enough, and I understand why. But it's insufficient to have just a sham, because we are manipulating the brain, and we're usually in the papers, just because of the historical accident of how the literature has evolved, making statements about basic science and about clinical possibilities within the same paper. And wherever the basic science is concerned, at the very least, we have to have active control sites and active control tasks. Best question I was ever asked when I gave a seminar is I showed these effects on transcranial magnetic stimulation and visual search, and then I showed some control tasks which I did afterwards, and somebody put his hand up and he said very unguardedly, on those control experiments, did you try as hard as on the other experiments? And I think it's a really, really fair question. And I think the truth is that we'd have to say no sometimes. There are some cognitive effects in the literature which get people in the media very excited. Snyder's creativity. I can't use the words on camera that I would like to use for that, but no. Hex decision-making task. It's one of my own in Journal of Neuroscience, and we did the same as these other papers. We had a bilateral montage. We didn't have an effective control task. Roy's task, the Frenny task, and also we've got to ask if we are having enhancement effects. Let's imagine that everything I've said is wrong. It wouldn't be the first time. Let's just imagine everything I've said is wrong, and all these experiments are great, and these improvements do happen. None of these papers have asked, and we don't ask in the literature. It's just not become part of our habit. Is to ask, well, what's the cost? Because it's a little bit like the way in which the brain imaging literature has allowed itself not to discuss bold decrements for 25 years. It's kind of rude to ask, and it's kind of rude to ask as well in DC experiments. Well, if this is what people are getting better at, what's the cost of it? It must be taking some resource from somewhere. And I think we're duty bound, certainly in a scientific sense, to answer that question. And I'd like to add to the point about the stasis in the MEP experiments, something called state dependency, a literature in the TMS literature, which I think has been led by Juha Silvanto, who was one of my PhD students. What he's shown is that you can completely reverse cognitive and perceptual effects with transcranial magnetic stimulation by manipulating people's perceptual or cognitive state before an experiment. So if I adapt to red, let's imagine you stimulate my visual cortex and make me see flashes of light, and I adapt to red, now those flashes of light are going to be red because you've changed the relative gain states of the red-green system and the blue-yellow system in the visual cortex. And I can't think of many papers outside of that literature, and I can certainly think of none in the DC literature that have tried to address what is the baseline state of the cognitive system in any experiments. I know it's not an answerable question, but it has to be something that we're thinking of, because we cannot assume that everything from a stable, relaxed motor threshold translates to the excitation and the inhibition states of the cognitive system. So what can we say? I think we can say this, rather than some. I think based on the best available studies from reputable laboratories, we don't really know where to put the electrodes. We don't know how robust is the idea that the effects are excitatory or inhibitory. We don't know what the other behaviours are that are affected. We haven't tested the methods with real-world tasks, and therefore we don't know how they perform outside the laboratory. Obviously there are some, but it's a very small part of literature. We have no idea in healthy people how these things continue to work after 2 or 3 repeated applications. I'd extend that to 5 replications. But I think that was such an important thing to read that I wrote it, and it's in an editorial that's coming out in Brain Stimulation. And of course it's over-egged, but I think it's got to be over-egged because the field is at such a intellectually lazy place that I think the signal-to-noise ratio is in danger of becoming even lower. And the cost of that will be to the people who we think we're supposed to be helping in the... When Roy was showing the experiments of all the enhancements, I was going through my literature collection as fast as possible to find out which ones of them fell foul of this rubric, and most of them did. Most of them did. I could only find. I only had time to copy one figure from Agnes Floel, who is as good as anybody else. But these effects of 5%, it's very hard to translate those to the clinical world. I was going to finish on one other study from my lab, but it makes largely the same points, but it makes it with transcranial random noise stimulation. I want to finish by introducing two other techniques which have not been mentioned. They're mentioned on one of Vince's slides, but not been discussed at all. Transcranial random noise stimulation, you do it with your machines, yeah, the Sotorix machines? Yeah. You can do it with the same machines as the DC. It seems to have large excitatory effects. And what we did here was, just to ask, we're going to answer the first question, is training plus stimulation effective in the young and the aging brain? This was Marinella Cappelletti who thought of and carried out and wrote this paper, so I don't know in what sense it's mine. I'm associated with it. And we trained people on a numerosity discrimination task, and they had to say whether it was more yellow or blue, and then they would get feedback, and they get several hundred trials of this over 5 days of training. So there's the task, and you all got it correct, or else you wouldn't be in this university. And we gave them 5 days of training, and had a young group, average age 25, an older group, average age 65. We committed the sin of having left-right stimulation as well over the parietal cortex. But we did show that let me get to the data because I do want to talk about the other things. We did show that the older population got as much benefit from learning this task. The thresholds for detection decreased as much as the younger population. And the question I wanted to raise on this is, do we now run off and say, right, everybody over 55 or 65 who wants to go to night school to learn should have transcranial random noise stimulation so that they can learn as well as the younger people? Or does it just mean that we can say to the public, what we've demonstrated here is that there really is that capacity in there, and the face validity of that might be sufficient to make people work a little bit harder, rather than have a technological solution to their learning difficulties. I have a vested interest in the belief that the greatest intellectual loss in society at the moment is in the middle-aged population. That's where all the lost talent is at the moment. And my answer is, of course, no. And going back to the very first study of brain stimulation and mathematical cognition, some of the voices from subsequent from that have started to ask, well, should we be stimulating children who might have some mathematical learning difficulties? And I would say, should we give them 100 hours a year extra maths lessons like the Japanese do? Wouldn't that be a reasonable idea to think of? So even though we can do, let's imagine again that I was wrong about this and that the enhancements really were there for transcranial direct current stimulation. There may be no more than proof of principle that ability is there, and there might be really great low-tech ways of getting those enhancements. So, I think I've made the points about the sham being insufficient, our mechanisms not being really, our explanation not being really mechanistic because the most prominent montage is poorly thought through. Our dependent variables don't really translate very well to the things that we talk about in our discussions. This isn't unique to DC stimulation. You know, we do it in the psychology literature. You give people a red circle and a blue square and lots of them on the screen, and you get them to detect the red circle amongst blue circles and red squares, and you get all excited about the reaction times, and then you write a paper when looking for a friend in a crowd. You know, how many of your friends look like it? We do it all the time. Yeah? So let's talk very briefly about another method very closely related to transcranial alternating to direct current stimulation. That's transcranial alternating current stimulation, in which the current that you deliver is alternating. And there's a growing literature using this, and I think given the interest in the functions of oscillations, and the very last question of Vince's talk was about when to stimulate and was consolidation a good time to stimulate. And in the sleep literature, there's some emerging evidence that stimulating with AC stimulation during slow wave sleep might be a good way to enhance consolidation. But that's one of the parameters that we haven't really begun. Again, the fact that people usually turn the stimulator on 5 minutes before the onset of the task and then leave it on for the 10-15 minutes during the task, that's a historical accident. There's no principle there of thinking about how DC stimulation works best in concert with the task. Another blurred one, I'm sorry. So here we don't have to worry about excitatory and inhibitory. Alternatingly, both electrode sites are that. Just to give you one example, this is from Ryota Kanai, who was in my lab. When we stimulate, so we're stimulating over the occipital cortex now with alternating current stimulation, and we're stimulating at different frequencies in the alpha, beta, gamma, delta and theta ranges, and you can see that when you have your eyes open in the light, your report of these, I can't remember how many subjects, your report of the intensity of the phosphines is biggest in the beta range. You still see them a little bit in the alpha range, but really it's in the beta range. These are just different intensities to titrate the intensities. And when we stimulate in the dark or blindfolded, the reports of those phosphines shift to the alpha ranges. So just a little example of frequency-specific effects. And also in the AC literature, an effect from Zahler's lab in, I think, Oldenburg, in which they gave AC stimulation in the alpha range at a subject's individual alpha frequency, and then looked at alpha power after stimulation. They had a sham group as well. They didn't have another frequency range, and alpha power in the individual range was increased after that entrainment by AC stimulation. I mean, we could hopefully, in a couple of years' time, have a whole other meeting where I'll tell you why the AC literature is bullshit. Where we could have a whole other meeting where we discuss the use of AC stimulation, because I think there are great things to be done with manipulating the oscillatory state of areas. In ethics, I'm sure it's going to come up in the decision. I've got 5 minutes, 4 minutes, 3 minutes, 2 minutes. There's always in the literature something about us either being able to read minds. The Guardian, a newspaper in England, had a whole page, nothing else on the front page a couple of years ago. Not even any football. I didn't know where to look. A whole page on an fMRI study showing that we could read minds, and of course we can't. But we're reaching the same stage in our hype cycle with DC stimulation, where increasingly we see in the press that we can improve people's memory, attention, any other number of things. And this has led my friend, and he's still my friend, despite this exchange of editorials in brain stimulation, Simone Rossi from Siena and others, to write an editorial arguing that it's really time to start thinking about legislating and regulating the use of DC machines, because we can have powerful effects, and it might affect things like gambling behaviour and have social consequences. I've written a companion editorial which kind of disagrees with that, and really it's based on the fact that we can't have powerful effects on the brain. Everything that you've seen today in the behavioural domain and everything that you've seen in the physiological domain are hard-won data points. Even though I've criticised them, they're hard-won data points in which people have done pilot experiments to find exactly the right conditions to get those very small effects. And as long as it's in a dark room and people keep very, very still, that's going to happen. But in the gaming world, when people are drinking Coke, maybe smoking cigarettes, maybe smoking other things, wandering around the room, talking to their mates, saying, hey, have you seen this thing that I've got on? It's going to enhance my gaming. It's going to have a pretty short shelf life, because economics will find us out, because it is not going to work. And it's not going to work for another reason in those domains, because it's going to demand people's compliance and return and effort. And the kinds of people who want big, fast gains are not going to do that. Which brings me to one final point, which is when we make our, this isn't it, I've just lost it, that's why it's my final point. When we make our experiments, we put an advert up, we say, person wanted for brain stimulation experiment, $7 an hour. And then we do an experiment on risk and decision making. Do we really believe that we haven't got a self-selecting population who think, ooh, brain stimulation, I'll go for that for $7? So we really have to ask what our baseline of knowledge is for all this. And again, this just finishing off by referring to Vince's talk, he talked about Berger possibly thinking about clairvoyance and precognition, and I think that is a field that DC stimulation genuinely can contribute to, and that there are some very, very good evidence that people can be given precognitive powers by DC stimulation, because I know exactly what you're all thinking right now.